Okay. Good evening, everyone. It gives me great pleasure to welcome you all to today's faculty development program. We are privileged to have with us an esteemed scholar and researcher, Dr. Roy, who will be sharing his expertise and insights with us today. Today's session promises to be both engaging and enriching, offering us valuable knowledge that we can apply into our respective fields. I would like to express my gratitude for the graceful acceptance to deliver this lecture, sir. And also, I would like to express my gratitude to our Managing Director, Dr. Maria Wilson, Principal, Dr. G.R. Suresh, IQAC Director, Dr. Shenbahayalil, Academic Dean, Dr. Shantini, for their encouragement and support. Before we start, I invite Ms. Akshaya to share the profile of Dr. Roy.
Marvelous evening to one and all present here. It is my distinct pleasure to welcome Dr. Anurag Rai, a visionary leader and innovator in the realms of renewable energy and material chemistry. Dr. Anurag Rai's distinguished career spans over 6 years of cutting edge research, where he has made remarkable strides in advancing solar energy technologies through the development of highly specialized nanoscale materials for net zero energy solutions. His work is at the intersection of science and sustainability, particularly in the fields of photovoltaics and smart materials for eco-friendly building design. Dr. Rai's illustrious career is marked by prestigious fellowships, EPSRC Research Fellowship, Marie Curie Research Fellowship, and the Commonwealth Research Fellowship, reflecting his influence and collaboration within the global scientific community. A prolific author, Dr. Rai has published several influential books and over 80 peer-reviewed papers which have garnered around 2000 citations. Beyond his research, Dr. Rai has played a pivotal role in bridging academia and industry, leading projects that have translated innovative concepts into tangible, impactful solutions. His dedication to mentoring the next generation of scientists and researchers further underscores his commitment to excellence. We welcome you, sir.
Yeah, thank you, Akshay. Should I start my session?
Yes, sir.
Oh, thank you. Okay, hello everyone. I'm Dr. Anurag Roy, and there was a vast introduction. So, okay, thank you so much for making me so glorious when I hear about all this. I was just little busy today. I'm still in the lab. You can see me. We have a very big uh, what the spray coater unit is installing, and I'm just busy with their paperwork and all the installation process. So forgive me if I'm in hurry or you can see me in exhausted. So sorry about that. So no more wasting time on talking. So let's focus on the topic. And here I'm going to share my screen. So just let me know. Yeah. So hope it's visible to everyone. Can someone confirm me whether you can see my
Yes,
screen
sir.
or
Yes,
not?
sir. Yeah,
Yes, sir.
it is
Okay.
Yes, sir.
visible.
Okay.
Yeah.
Thank you so much.
Visible.
Yes. So, first of all, again, thank you so much for inviting me for this wonderful faculty development program initiative, and thank you, Dr. Sarojini, who is personally emailing me and asking me to come and share my research knowledge and a bit of materials discussions over here. So thank you for giving me the opportunity. I'm glad to be presented here. So today I'm going to discuss about the functional nanomaterials for solar induced translational material research. So if you just very carefully look at my today's topic title, so I'm going to focus on three keywords here, which will be covered up throughout my discussion. So number one is the functional nanomaterials. What's that? And how we can include solar-induced translationality, and later how material research is involved to bridging the gap between functional nanomaterials and solar-induced translational research. There is nothing more to discuss about my professional career background, but just I make a slide to all of you to have a look. Who am I actually? So I'm currently as a EPSRC research fellow working in the University of Exeter Solar Energy Research Group, which is in the southwest of the England, which is it's called the Cornwall. And before joining or getting this fellowship, I was in industrial impact fellow under the Agritech Cornwall project, and I did my master's, bachelor's, all from including PhD, all from India. You can see here. I belongs to Kolkata, which is in West Bengal, eastern part of the India, the only city in the world where you can see six Nobel laureates from six different categories. So I always share this one to everyone. The city where I born, brought up, and did my preliminary education. And if you want to know more about my research and related topics and about the discussions, please, I'm available in Orchid, Google Scholar, LinkedIn, Facebook, Twitter, I mean all the social media. So you can follow me over there and happy to chat with you. Okay, so what's special today that brings all of you here to join this session? So when we talk about faculty development, a big role of a faculty is doing research. So beside the teaching or the academic responsibility, research is one of the pivotal, a trigger point of every academics that can gives you more pleasure compared to the other duties, what I feel as a researcher. So when we talk about research, do you think that research means just to Google it, or just making some methodology and some idea that can be easily developed using a web browser, but technically it's not. So what's exactly a research? So a research is, it's we call, if you look at this image, we call it a potato cycle. So let me take the pointer screen anyway. So what is potato research? So it's all about a circle which we are following. So we need to understand, so what is the facts and find, followed by we need to establish a methodology, including the methodology that helps you to develop an idea. So giving or developing an idea is very important, and that can be going to a practical emplacement. So when we did the practical emplacement, the further stage is the treatment of that emplacing strategy, and then you get a result. So the result may be good, may be bad, or may be moderate. So accordingly, we need to go back again our facts and finding, and again we need to set up the methodology and again follow the similar circle as you can see in this picture. So this is why what in UK we call it potato research. So it's a circle that we need to find out. If any problem in any research happen, just follow this circle so you can get the best outcome of it. So what we gonna, as it is a training program, so I just put these slides for all of you. So what we gonna learn, what is the intended learning outcome of today's sessions? So after today's session, we're going to understand and apply some fundamental principles of nanomaterial science in the context of solar energy applications, where it includes the synthesis, characterizations, optimization of nanomaterials for enhanced solar capture and conversion, followed by evaluation of performance of various nanomaterials in solar-induced processes, such as I will discuss that when we talk about solar energy, it's just not strictly to photovoltaic, which is very common and making a taboo, but at the same time, solar energy has many other applications. For example, solar thermal, photocatalysis, and photodynamics regarding applications. So we will discussing and analyzing how their efficiency, stability, and scalability is important in terms of material science. We're gonna translate experimental findings into practical applications by integrating theoretical knowledge with hands-on experience. I mean, virtual hands-on experience, the the design of prototypes and assessment of their real-world acceptability or applicability, whatever. And finally, critically access recent advancement and emerging trends in functional nanomaterials for solar technologies and articulate the potential impacts of this innovation on the future of sustainable energy, which is a very crucial point nowadays, sustainable energy, net zero target. So how we can deal with that? What is the idea of we can develop at this stage of research? So whenever I start any session or whenever there is some discussion topic come out, so it's definitely go for loads of WH questions. So for today's sessions, definitely we're gonna cover up or try to cover up all these questions, which is mostly related to why we choose nanomaterial, when it comes to focus, where it stands, how it works, which is the right way to deal with, what is the utility of it, do we understand it or do we interested about this material, and of course the big question, is there any future of it? So to start any research or any kind of research or development activities, we need to get some motivation. So where we get the motivation of our work? Now go back to the nature. Nature is a big inspiration for all of our activities. So if you can look at the right hand side image, you can see brain cell versus universe, birth of a cell versus death of a star, and an eye image versus nebula. Did you find out what is the similarity between these two pictures? You can see human mind, human structure. As a human, whatever the components available in our body, it's just similar to whatever is there in the universe. It's very, very closely related. And you can see there is an evidence in this picture as well that how brain cell structure or its networking is quite similar to the how the universe is actually distributing. Similarly, if you just look at the left-hand side of the slides, that when we develop the human brain, the brain actually understand three parameters: color, shape, and music. So as a researcher, we need to think that how we can develop a good research or how we can develop a mind-blowing material or a discovery, innovation, whatever. But we need to first fundamentally or at a very ground level, we need to think that how this color, shape, and music is affect our brain. And that is why your this is a trigger point, or this is a very fundamental base of your thinking level, how you critically think, how we critically think, or how it makes us different than other people. That is why you can see being a researcher, or it's very challenging when we say the novelty of the work. So how the novelty comes and how to bring those novelty, that actually we need to think from our brain. So how this brain works, that's also matter, and that gives also a motivations to do that. And nature is a big example out of it. Now, come to today's core topic, which is, as I discussed, nanomaterials. So, when we talk about nanomaterials, there is a big question comes that why there is so much interest on nanoscience and nanotechnology, and what lies ahead. So if somebody is not aware of nano or the nano term, so for them, and I guess everybody's familiar more or less with this term nano, but at the same time, the nano is an unit. So the only unit or the exclusive unit where the material's property just may massively change compared to its bulk form. That is why particularly nanoscience or nanotechnology, this term is on focus. You rarely seen or you rarely heard about pico technology or maybe picoscience, hectoscience, kiloscience, gram science. No, nanoscience, because it is the only unit where the material's property drastically change compared to its bulk nature or bulk form. So the common example of nanoterm in our daily life you can see in SIMs, the mobile SIM. So a standard SIM, micro SIM nowadays is called nano SIMs. Similarly, there is a common car. It's cheaper car in India. It's called a nano, developed by Tata Group. And at the same time, you can see here how the nanoscale makes a drastic importance of our characteristics development. So the term nano, why it's called nano, it's linked with not only our internal or very fundamental system, it's also now making a brand. So using the term nano, including a SIM or either a SIM or a car is become very popular. You can see it's now become more a brand. Now, how do you think this nano makes importance and why not meter? As I discussed, as I mentioned previously, that nano material have different properties compared to the same substance in bulk form. What does it mean? It means that a material could change when it goes from bulk to nano form, but what size that happens varies depending on its substance. So for example, the real-time example that you can see, any guesses what's this picture is about? This is a picture of human hair, our hair. I have less hair, but anyway, those who have lots of hair, you can see it in a microscopic image. So this is a human hair ACM, and you can see that how it distributed. This is a lotus leaf. So if you look at very closely lotus leaf, you can see its hydrophobic surface, or in general, what we call the water repelling properties. A lizard, you can find most of the houses walls, and how a lizard stick on the wall, that is also including a nanoscience. And all these things are related to the aspect ratio formation. How large is your nanoparticle or rather nanostructure, and how major area it distributed, the ratio between these two parameters decided its aspect ratio. Now, there is a debate, of course, and of course, there is a strong reason for this is the quantum confinement effect. I'm not going to details. This is a more hard topic and need another session for discussion. But quantum confinement effect is an effect mostly where the electron get a restricted position of movement. That's what the property evolve. This drastic property change can happen. And for your generalized interest, let's say from 1 to 100 nanometer is called the nanoscale region. If anything lower than 1 or higher than 100, it's not to be considered as nanomaterial. They have their separate categories, but usually this is the ideal range. Now, how this nano science and technology evolve? Before going to that one, I just want to share one interesting story, which is from UK, definitely, and that reflects that how science is very, very simple for us. For example, I'm just showing, by the way, you can see here the nanotechnology and the nanoscience. This nano terms has been first introduced by Professor Richard Feynman in 1959. And then he got the Nobel Prize in Physics in 1965 by the but interestingly, the story of graphene, if you don't know about that, that how graphene evolved, what is the history of graphene and how suddenly graphene as a material becomes very popular in the world. And nowadays, everybody more or less working or familiar with graphene. So Andrew Cream and Konstantin Novoselov from the University of Manchester in UK, they won the Nobel Prize for discovery of graphene. And very interestingly, they just get the graphene from a pencil. So a pencil contains that the lid of the pencil, the tip of the pencil, sorry, is contained graphite that we all know, lead-based graphite sometimes. So by exfoliation using a scotch tape or sellotape, usually in UK we have scotch tapes, they develop the graphene layer because graphite is a stuck of material and exfoliated one layer is called the graphene. And see the idea that how science is simple and how it works. And you can see the trends of nanoscience and nanotechnology compared to the other various disciplines is quite progressing, faster progressing, very steep rise among the rest of, I mean, in last 10 years, 20 years. There is another quick example that how you can understand that importance of nanoscience, that your finger, you can see our all the fingernails can go up to 1 nanometer per seconds. So if possible to measure our nails every day, and you can see there is at least 1 nanometer progression of our nail length every day if we can able to measure it. So, what makes nano so special? So, as I mentioned, that nano material or any material which comes to the nano form, it changes property drastically. Here is an example you can see. So, 2 gram each TiO2 nanoparticle, and you can see that the 2 gram is distributed. I mean, 2 gram for all in 4 bottles. And interestingly, the high packing density. So this is the standard bulk TiO2, and you can see this is at the nano TiO2. Okay, so each are 2 gram, but their packing density is so high. So 2 gram for this material is that much. And when it comes to the nanomaterial using CTAP, SDS, DTAP, different chemical synthesis, what we applied to develop a nanoparticle. So that causes the high packing density. Now, there is some pros. And there,
Ex- Participants, kindly turn off your audio.
okay, so if there is a pros, there is some cons. What is the problem with the nanomaterial? So nanomaterial cause or a high degree of causing agglomeration. So you can see that if you produce some nanomaterial, there is a high chance of agglomeration because of their small size. And aggregation sometimes causes amorphous characteristics. That's what you can see when you go for X-ray analysis of your nanomaterial. You can see more, I mean, or higher peak to noise, noise to peak ratio, noise to signal ratio compared to a bulk material. And if it is too small than the detection level, it sometimes never be accurate to measurement. And last but not the least, the phase purity. So if you want to develop some complex material in its nanoform, phase purity or the phase development is a very crucial factor. I will show you in a couple of seconds in some other example. Now, how we can link now these nanomaterials or this nano concept with solar energy? I try to make it very simpler so that I'm not sure about the disciplines of the audience. So taking considerate that all the audiences are familiar with a bit of nanoscience and chemistry. So I just want to make a general pattern so that everybody can apply it in their individual field with this mechanism. You can see when, so for example, this is the band gap. I hope people understand the band gap, the semiconducting band gap. So when there is some light interaction, or what we call the excitation process, right? When the photon absorbed by a material and it get excited, the electron excited. Now the electron in photovoltaic, what happened? The electron goes from HOMO to LUMO, or rather we can say from valence band to conduction band. So in conduction band, when the excited electrons moving, you can see here, so as a for example, photovoltaic research, we need to take out that excited electron to an external load circuit, and that is what we can get the current. That's called the photovoltaic. But what happened to other process if the electron is not excited, or if the electron is not taken out? If the electron, say inside the system, so they cause the fluorescence. And fluorescence or the emissions, which is in general emissions, has plenty of properties. It can be fluorescence, it can be phosphorescence, or it can be uh, any surface trapping. We don't know. So this is how you can see that light interaction helps. The how much light is interacting and how fast it can generate the excited electron and become emissive. That's what the system works. Another interesting thing is that the surface functionalization. So how the nanomaterials or nanosystems can work with different surface functionalized system, and how it works with a particular application that also important for this nanomaterial surface functionalizations process. Now, as I mentioned, there is a very confusing thing. So functional nanomaterials and multifunctional nanomaterials. So what does it mean? So when we talk about functional nanomaterials, that means a material which is a nanoform, which can dedicatedly work for only one application. But at the same time, when that material can be work for different application, that's called the multifunctional. Not only that, it's not about different application, it also about different property evaluation. For example, if a nanomaterial is initially just only what to say, nanomaterial has high surface area, for example. So if a material has high surface area, so it can absorb, say, more pollutant. For example, it can absorb more air pollutant. So that is what. So to absorb more air pollutant, you need to develop high surface area material. And to get a high surface area material, you need to transfer your material from bulk to nano. Clear up to this? Now, if a material is high surface area, they can, for example, generate high amount of electron when it interacts with light. You see, not here is double property. So it's not only high surface area. When there is a high surface area, this high surface area makes the materials to get more electron from the sun or from the light to show its photocatalytic activity. So same material showing two different properties at a single time. That's called the multifunctional nanomaterial. So here is the difference, functional and multifunctional, and completely depends on the mechanism, the process, and the results and analysis what we are explaining or what we are proving or evidencing. Accordingly, we need to coin out, or we need to disclose our material is a functional or multifunctional. Next is the how we get this material in our laboratory or in practical life. So two things, structure and synthesis. So when we develop a nanomaterial, you can see I rarely use the term nanoparticle. So I mean to say that nanomaterial. So a material can be anything. It can be a particle, rod, flower, 1D, 2D, 3D, 4D, any shapes. So it completely depends which shapes as a user, as a researcher, I'm looking for. Okay, so there is a three major process of synthesis of these nanomaterials. One is physical, second one is biological, and third is chemical. So what is physical? So physical method is where we rarely use any chemicals or going through any chemical hazardous process. It usually a thin film based, and if you're familiar, the physical methods are the ball milling, inert gas condensation, pulse vapor deposition, physical vapor deposition, laser pyrolysis, flash sprays pyrolysis. What the instrument I'm here trying to install it, we have a very big flash spray pyrolysis system. I'm just sorting out those things here. Anyway, electrospraying and melt mixing. Chemical methods. So this is a very common method, mostly we used like salt gel synthesis, microemulsion, hydrothermal synthesis, polyol synthesis, chemical vapor synthesis, and sometimes plasma enhancement, which we integrate with the chemical vapor synthesis or CVD process. And last but not the least is the sustainable process, which is the biological methods where we use the microorganism, biotemplating, and plant extract. But the problem, this method is definitely sustainable compared to physical and chemical, less chemical hazard, less pollution. But the problem of biological methods, it's very, very, complex and not getting a very selective or standard, product. So either your product formed in different phases or in different shape, or your product may not form properly what phase you are looking for. So that's the problem of biological methods. Otherwise, it is definitely a good method. And on the right hand side, you can see that how different structure you can form using this synthesis. So your chemical transformation of a nanoparticle is leading to alloy formation, galvanic replacement, cation exchange, anion exchange. So these are the some common mechanism through that the nanoparticle, or rather, sorry, nanomaterial is moving or transforming it to which shape they will create. It's a core shell or blah blah blah, all these things. Yeah. Now, how we can determine whether my material is nano or not? I have synthesized some powder or some samples. Now I have to establish, or I have to prove my sample is nanomaterial or my sample is in the nano zone. How to prove that? So this is we call the diagnosis. If I get some disease or I have some health issues, first of all the doctor go for diagnose me and just check that what is the problem in my body, and accordingly they will start the treatment based on my diagnosis result, right? So similarly, when there is a material we synthesize, we need to diagnose that material, what we call in scientific term characterization. So characterization is a kind of or similar to a diagnosis, where there are plenty of characterizations technique where you can prove your material is a nanoform. It can be XRD, it can be XPS, BT, TG. It's a long process, and there is a various categories of characterizations, starting from optical, structural, surface, others like electrical, magnetical, like this kind of elasticity, different kind of properties you can evaluate. So there is a different method that you can see here. I'm not going to details individually, but this is gives an overview that there is various spectroscopic techniques of nanocharacterization is available. Now here is an example that synthesis of zinc stannate via electrospinning technique. So electrospinning is a technique through that you can develop some nanomaterials. Here is a video, hopefully it will on. Yes, you can see that how we can fabricate a hollow zinc stannate, a hollow fiber using electrospinning technique. So this is an example that electrospinning is a technique through which you can produce some nanomaterials. And this is the nanomaterials, zinc stannate, and you can see this is a hollow structure. For more details, this is a paper, you can have a look, but I'm just trying to give you an example how it works. You can see how the fiber is producing using the electrospinning technique. And the material what we are looking for is a zinc stannate, Zn2SNO4. Yeah. So moving on to the next. So these are some different ACM, pardon, sorry. So these are some different ACM structures that we developed in our lab, where you can see different nanomaterial structures, starting flower, hexagon, what rod. I'm getting confused. So many structures. So cubes, I mean, 1D rod, composite rod. These are the nanoparticles. You can see this is a 2 nanometer or 2 to 5 nanometer nanoparticles, some flower structure, this type of structures. And this is a very basic example. Now, quickly, I will go through the properties of nano. This is a common example. Uh, in this case, you can see that in figure A, that there is a three plot. Just look, forget about the materials, just look at the plot. So it's a three plot, and it is basically magnetism plot. So in magnetism plot, you can see that there is some S sign of plot, and two different or three different types of S: red, green, blue. The formation of the S and the distribution of the S pattern is actually determining how strong magnet you have produced. You can see here S3 is 12.6 nanometer, which is the particle size, 10 nanometer particle size, and 7.2 nanometer particle size. As smaller is your particle size, you can see your S or the distribution is getting flattered compared to your big particle size. Another example, just next to it, you can see if you increase if you increase your particle size, or if you can vary the particle size, you can see different emission. This is the emission plot, fluorescence plot mostly. So you can see different emission is come for a single material. Material is same, but their particle size is different, that can exhibit different emission. Similarly, this is a dielectric constant. You can see the particle size is varying from 100 to 500. At the same time, your dielectric constant is also varying, which is disproportional. Here is the CV, or cyclic voltammetry plot. You can see the potential versus current, and you can see that 6.07 nanometer and 1.60 nanometer, two different particle size shows two different, uh, different types of CV pattern. Here is the capacitance versus scan rate, and you can see it's the same two different particle. It shows two different characteristics. This is the elastic modules uh, for the strain analysis, young modulus analysis. Yes, so you can see here it is there, and what else? And this is some optical property that's called with the absorption spectroscopy analysis. Same AU molecules. Oh, this is an interesting example. You can see here it is a particle. It is what kind of? It's a triangular particle, or a pentagon particle, and this is a rod. So three different type of shapes, exhibits three different types of absorption. Same material, three different. So here is an importance. It's called the effect of morphology. How a morphology can be effect in your application or in your in the particles property. Now, quickly, I will go after this nanoscience, that what is a material science. So a material science is an interdisciplinary subject spanning the physics and chemistry of matter, engineering applications, and industrial manufacturing processes. So what's the properties that we are searching in a material? That depends on how the material science field is developing. So you can see here that the strength, hardness, flexibility, thermal, magnetic, electrical. So these are, I'm not going to the details, but you can see the list that different properties that you can include in a single system, and that's it's called the material science field. For example, here I just showed, sorry, here is I just showed that silicon. So if you can take out sand from a beach, you can extract the silicon. Now you have a silicon in this hand, and other hand you just think about the nature. So what's the nature? In nature is a photosynthesis. So what is photosynthesis? The leaf absorb the sunlight and convert the light energy to chemical energy, which we call ATP. right? So take this idea. So this is a silicon. If it absorbs the sunlight and that silicon converted to light energy to, for example, electrical energy, which is in the solar cells. That is how silicon solar cells concept generated. So it's actually a natural inspiration from a leaf or the photosynthesis process, right? Here is the importance of the material science, how it can evolve. Now, typically come to the solar energy research, as I mentioned earlier, as I mentioned earlier, because solar is a bright future and all we are struggling to get a net zero analysis and one of the renewable energy technologies. So solar is the only renewable energy source which could in principle easily meet all world's energy needs because it's free. First of all, we don't need to pay for the resources, at least. Now come the point why we should choose solar energy. So solar energy is just not a renewable. As I mentioned, it can be photovoltaic, it can be photocatalytic, it can be photodynamic, it can be photothermal, any photo related process besides photovoltaic. But to deal with all this phenomena, all this, working activity, what we need a material. Here is the importance of the material science. It's just not like orally, verbally, or by theoretically possible. To make it practically, we need a material which can deal with our this type of application where we are targeting. So a very quick update, those who are not familiar, what is the current net zero emissions by 2050 scenario where the solar PV and the wind additions are the forecast to be the more double by 2018 compared with 2022, continuously breaking records over the forecast period to reach almost 710 gigawatts. And you can see here in this plot, I'm not going to the details, but it's quite common that solar energy is quite moving forward and giving a very high extensions for worldwide acceptance. And these are some critical points in terms of UK, that around three-tenths of the UK's energy was produced by wind power in April 2024. So this is, and solar energy made up to 4.5% of the UK's energy production in April 2024. I'm just giving you an idea that how UK is moving towards the net zero solutions and towards more depending on the renewable energy system. And also, it's very important when we dealing with net zero, we need to take care of the sustainable development goals. So currently, when we talk about solar energy, it's definitely a number seven, affordable and clean energy, but it doesn't mean that we should violate or we should ignore the other SDGs. So when we talk about net zero scenario, it's just not only the energy, it's also the other parameters in a society that we should consider alignment with the sustainable development goals set by UN. Now come to now my topic. I think I have half an hour, I guess. Just let me know if I'm getting so, or how much time I leave. Just let me know, okay? So some solar translational materials research. So what we are doing, I will go very quickly in 10-15 minutes. So in our department, in solar energy research department based in University of Exeter, Cornwall, we are mainly, I'm doing mainly with three research topic: passive cooling, photovoltaics, and wastewater treatment. So let's start with the photovoltaic. So we are working on the perovskite solar cells. So those who are not relevant to the perovskite solar cell, it is a third generation solar cells beyond silicon photovoltaic, where perovskite is a kind of structure, basically a calcium titanate structure, where we can make it from the all inorganic or inorganic organic kind of a structure. And due to change the structure from cubic, tetragonal, orthorhombic, different crystal pattern, its property change. And that is the benefit of this perovskite solar cells. But if you look at this plot, solar side is, perovskite solar cells is a technology where it takes just only 10 years to get 26% efficiency, whereas for silicon solar cells, it took almost 26 years to get the similar efficiency. So perovskite is a quite emerging research area right nowadays because it's very short time and easy to prepare in lab and get very high efficiency compared to silicon. Now, the problem of perovskite solar cell is its stability because most of the perovskite material contains lead, and due to contains lead, there is a very big environmental concern. And at the same time, it is lead based. Any material is quite aggressive to humidity and moisture. So that's what your material can be easily degrade. And especially when we talk about solar cell, it has to be in place in the real world condition outside of the building or the house. So definitely the stability. Yes. Hello.
Ma'am, ma'am, thank you. Sorry, sir.
Okay. Yeah, so this is our research. You can see here that we have developed some barium stanide based and brookite TiO2 based perovskite solar cells at ambient condition, which can show 15.2% efficiency highest, and different shape we used for our. Here is the importance of the nanoscience, that rod shaped and this kind of dumbbell shaped materials we used for the solar cells evaluation. Here is the paper. You can have a look for more details. That but the basic structure, the basic conclusion out of this, that this type of material can evolve as a new perovskite material, which is a bit of stable, not 100% stable, but a bit of stable, but showing a very high efficiency, 15.02%. Another one is the carbon, because most of the perovskite solar cells use gold plated system. So gold as a counter electrode, but we used because gold is very costly and we can't afford all the time, especially for large scaling. That is why carbon is an alternative source, and we use some sustainable technique to develop this carbon, which is from the cotton shoot. So this carbons is used for a back electrode, or we call the counter electrode purpose, where it shows a very good amount of, or very good efficiency enhancement is 13.2. And these are the different techniques, HTNC and LTCN. So you can get the more details on the paper, but this rough idea is the carbon can be a replacement and for perovskite solar cells. Another one is the temperature analysis, that how stable is our solar cells for long-term run. So if you just make a solar cells and just put some temperature, say 5 to 75 degree, and what is happened. So if you have a solar cells and you just go for a random, thermal treatment or the thermal analysis or a long-term thermal analysis, what kind of electrical impact and how the materials degradation start, that is also a detailed study we have done. Another one is in terms of perovskite materials, which is a common one, is the MAPBI3. So as I mentioned, lead is toxic, so we want to, or it is recommended not to use lead for that, and but we can't get rid of lead so quickly because the property of the lead is not replaceable by any other metal. But still, we tried with some sort of copper. So we replace lead with some coppers, and we try copper replacement in various ratios. And here you can see that how the copper replacement makes an impact when the perovskite structure shifts from lead based to lead copper based to only copper based. Another one is the dye sensitized solar cells. So instead of perovskite, you can use a natural dye or you can use a synthetic dye. And here I want to show you some effect of morphology, how the nanomaterials is important. So one is cubic, one is particle. So if you can change your morphology and if you can change your shape of your particle, that can make a direct impact of the electrical performance. Similarly, this is also a barium stanate using different morphology. You can see particle rod, exfoliation rod, and some kind of strip. So how this morphology can have a direct impact on the electrical performance of a solar cells that you can see over here. Next, our group is very well known and renowned for the concentrated solar cells. Due to the time shortage, I'm not going to the individual details, but a concentrated solar cell is a concept, is a strategy where we don't need to use big panels because of the maintenance, because of the large scale production challenging. So what a concentrated solar cells using an optics, it can be a lens, it can be any formulation optics that can you integrate in a solar cells in such a way, in a very small tiny solar cells in such a way that the light concentrate through the lens and concentrate into the small cells and generate 300 to 500 more power than a big panel. So you can save the space, you can save the money, and uh, also the maintenance cost. So this is how the system work for the concentrated cell. And there is a different optics. You can see in our lab, our other researchers has working on that. And here we developed the perovskite solar cells, but first time that perovskite, the solar cells and different optics, how it can go for glow concentrated perovskite solar cells performance. Also, we have developed some Fresnel lane space perovskite solar cells certified in a collaboration with EPFL Switzerland. So you can see here that how this solar cells is actually made and how it workings depending on its focal length variation, solar irradiation variation, how the system is stable and getting more power. Here is the electrical performance that with optics, different focal length, how much power you can get. As I mentioned, see, without HCPV, I mean, for example, without optics, your efficiency, your power is here. And when you get the optics, you see your power is changing. And after that, it becomes saturated. That's common. Also, we did some testing about thermal analysis. As I mentioned, if a solar cells has a long-term exposure of any heat, there is a thermal degradation, how it impact the solar cells performance or the materials interconnections or inside the materials interjunctions that we have studied through even real-time study with the FTIR cameras as well. Here is a good review who want to new this field and want to explore some idea about the concentrated photovoltaics for perovskite. You can have a read of our review published in APR. Uh, Quickly on passive cooling, which is what is passive cooling? So passive cooling is a kind of technology. Specifically, I would say it's a window. So through the window, because why it's window? Because window control our house's energy level up to 20 to 30%. So that is why what I'm doing currently is the smart glazing research, where our target is to make a smart energy system, or rather say smart window system, which can control the room temperature in a such a way so that we don't need to turn on an AC or a heater depending on or irrespective of outside temperature. So that is why we can get rid of any electrical appliances and we can save a lot of energy bill. Just you need to make sure your window is working well. That is why we call the passive cooling technology. So here you can see an example that here is a window coating, a glass coating with this material SNO2L2O3. And I'm not going to the individual details, but give you some basic and estimated idea that if you use this kind of composite coating on a glass surface, your outside temperature, if it is increased, your inside temperature, it's see if you're outside, look at my cursor. If your outside temperature say 45-degree, your inside temperature still remain 30-degree. At the same time, if your outside temperature is say 80-degree, when you put the glass inside your house, your inside temperature or the room temperature is quite low, 25 to 30-degree. This type of glass coating. But if there is no glass coating, normal glass, which is commonly used in our houses, that is why there is no heat difference. And that is why we need to turn on an AC if there is a so much, high temperature. We don't want to use AC. It's just a strategy how a window can be, because why window particularly? Because window has a major role in our house, which can go for 30 to 40% heat exchange compared to other part of our house. And not only that, window must be visible. So we can get a visual pleasure when we see, when we open the window, get a fresh air or see the outside. That gives, not the roof or the wall. They don't give a visual pleasure at the same time. So window also linked to our mental well-being. Here is another example of that indium oxide and zinc oxide based multifold smart glazing composite, which you can see that how it affect, and the outside temperature and inside temperature gradient, what we call. And not only that, this is an example of the multifunctional nanoparticles. So why it is multifunctional? It not only control the temperature, it also gives a self-cleaning property. So same materials giving two properties at a time, it's called the multifunctional. So it gives a water resistance property as well when you use it in terms of a coating. We use some perovskite material as well in a smart glazing solution. So where you can see that thermochromic. What is thermochromic? The perovskite materials change its color according to temperature, and that gives a temperature gradient when you use this material as a solar window concept. And finally, we use some hydrogels. So hydrogel is a very common material for the drug delivery and the biomedical application, using for lots of biomedical fields. But I tried to bring those properties of hydrogel into window. Interestingly, that's really very funny story. But those hydrogel have a very unique property, that the hydrogel change its structure in a such a way it can actually making a thermotropic level. So what is thermotropicity? So according to the temperature, if a material changes shape, and that can control its temperature gradient. So that is the unique idea, and that we have tried to build this hydrogel property in the window. So instead of a coating, there is a glass, and we are filtering with some hydrogen, or infiltrate the hydrogel in between the glasses and use that concept as a smart glazing system. You can see here, for example, that how it changed. So outside is 50-degree, inside is still 20-degree. Outside is minus 10-degree, inside still feel 10 degrees, so quite warm. You don't need to go for electrical appliances. And here another one is not the window, is just a wallpaper. What we when I was doing the Agritech Cornwall project, yes. So here you can see we have developed some graphene wallpaper. Graphene, the noble one, again back here. So the graphene has a high tendency of high heat absorption, at the same time high electrical conductivity. So we've developed some graphene wallpaper. So what's that? This wallpaper, if you just stick on the wall or stick on somewhere, if you the project was initially for the cow burns, where the cow stays, and for the high milk production of the cows, because cows are having a very high amount of heat stress, and they are started panting. So to maintaining, or to don't use a long big fans inside the dairy, so how you can make a wallpaper that can extract the heat out of the cow, and they can store for a long time, and that you can reuse for nighttime evaluation. Another one is a concentrated cell. I'm not going to the details, and you can see, yeah, you can see this is interesting. When you use this kind of wallpaper and under the concentrated cell under a concentrated light condition can generate up to 500 degrees Celsius. In the lab, when you see in the 500 degrees Celsius, that immediately break the glass. So that is what this research was about, and we discuss in this paper about this effect. We study theoretically and a bit understanding about the building integrated photovoltaic research. We choose five different location in polar, temperate, tropical, semi-desert, and desert location, and try to understand that how the environment, the real-time environment, make a big factor when we are talking about perovskite solar cells, BIPV integration. And here is another example that all carbon-based solar cells that we use for building integrated, and also the dye-sensitized solar cells that we tested for, I think, two years. Yeah, of almost 2 years. That how as solar cells, when you develop a lab and test it after 2 years, what is the effect, real effect out of it. Due to the time shortage, I'm not going to. So we are also working that with the biomimicry concept, that how we can get inspired from nature. So how nature help us, and how natural things can be you know make us for the biomimicry nature. In future, we are thinking to do some nature inspiration where the biomimicry can be developed through the diatom solar cells, Fibonacci sequence, solar heliotropes. These are the different technologies where we used for the solar energy research. You can see some natural examples that how you can get an idea to develop your nanomaterial, and also some leaf structure, light strapping method, and mechanical solar cells. It is very interesting that, for example, you see the sunflower follow the sun, and accordingly they bloom. When the sun gone, they shrink, like their petals shrink. Similarly, we try to develop a solar cells which follow the sun. Currently it not follow the sun. When the suns move, the solar cells still static. But if the sun moves and the solar cells also move, we are trying to develop this kind of system. It is still in nature, you can get the similar pattern, but not in practical in human life. So we are trying to get the idea that how this system work, how this connection work, and trying to develop. So this is the biomimicry for solar energy part. And finally, I'm almost concluding my session with some technology transfer information. So we have a here spin out company called the Build Solar, who developed this CPV solar brick. You can see this brick. This is a concentrated cell. So instead of big panel, if you just use a small cell in your house, they give you 200 times, 300 times, depends on the size and optics for characteristics, but at least 2 to 300 times higher power compared to a big panel. I'm also working with the World while the foundation WWF in India in Sundarban area, where many people doesn't have still electricity. So I'm raising the charity for them. I'm helping them with my solar research, whatever funding I'm getting. Recently, we distributed, I think 80 to 100 solar cells we installed in the Sundarban area. It's a very poor and remote area in the West Bengal, in the Bay of Bengal region. But that's very important for our biodiversity, because all the storms are covered due to the Sundarban Delta, and only this is also a UNESCO site. Anyway, we are working on the Pilkington glass, one of the big company of the glass production system. We are trying to develop some sustainable glasses, because glass industries still make a big impact of the carbon emission. So we are trying to deal with that. I'm also give some teaching things with the University of Exeter Business School, where biomimicry for energy module, I'm taking care of it. So it's mostly a 3 years course. So in the second year and the third year course module for I think 20 hours, I need to take a class, and the workshop that this is, you can see the how the students are preparing the dye-sensitized solar cells during the classes. And of course, recently I have been to the British Science Festival to demonstrate all over my work in terms of the prototype. I don't have here currently, but we can see, we can engage with the public directly, that what I'm doing or what our group is doing for the society. And finally, some take-home messages that innovative material, they are basic chemistry and physico-chemical properties, sustainable development and technology transfer. It's a cycle. So when we develop a research, when we're thinking about a material, that we need to consider its technology radiance level pattern. At the same time, it's also sorry. At the same time, it also gives us an opportunity of the interdisciplinary research. If you are interested for any interdisciplinary research, for example, if somebody is very expert in crystal structure analysis, somebody is expert in the degradation and microbes photovoltaic, or somebody interested for the image analysis, please come back to me. I'm happy to collaborate, or I'm happy to discuss if you need any help. Not necessarily always collaboration. If you need any suggestion, you want to discuss anything, I'm happy to give some shade on it. And finally, yes, thank you so much for your kind attention. I think I took a bit longer time, but I have been assigned. So I'm sorry for that. And thank you so much for your kind patience and attending today's session. I would love to take any question if you have. Thank you.
Thank you, sir. Really, I am very proud as an Indian uh, for your vast contribution to the society, sir. May God bless you and keep you blessing for many others in future also.
Thank you.
I want to uh, thank for your graceful acceptance once again to deliver the talk.
Yes, thank you, Dr. Sarojini. It was a pleasure to meet all of you. Although it's a virtual, but still, I feel that anything comes from India, I always say yes. So thank you so much for having me here.
Actually, your deep knowledge was not only informative, sir, but also very inspiring one. You are a very good teacher, also. Very lively talk.
Thank you.
you are. You have given a very live talk, sir. Uh,
Thank
a
you.
lot
Thank
of
you.
visual pictures and very interesting and engaging talk. Truly, we appreciate the time and effort you look to share your expertise with us. Your contributions really enriched this program and provided valuable insights that will undoubtedly benefit our teaching and research practices. Thank you so much, sir.
Yeah, it's just a quick note that whenever in UK or in our university, we need to follow evidence-based teaching always. It's not just theoretically. We just say this is a example, or this is a what to say, a definition of something. No, we need to show real-time evidence also. So that makes the teaching more attractive, and also engagement, so the people or the students mostly get some kind of critical thinking mind. Otherwise it will be very regular teaching. So we don't need to follow that. So to involve the students also for critical thinking and sharing their experience, I always ask my students to or any, it's not necessarily in the class. If I'm a supervisor of dissertation of some PG UG students, I just thought, what do you think about it? I need to know first what their first impression about the course or the topic. So that gives an idea that what's the student's thinking level and from where I should start my level.
Thank you, sir.
Thank
We
you.
are
Yeah.
looking forward
So,
for further collaborations in
yeah, yeah, of
passive
course.
research and also biomimicry, solar energy, and
Mm.
everything.
Sure. Thank you. If anyone has any question, I'm happy to answer it.
Sir, good evening, sir. This is Kalidas.
Good evening,
Hello.
Kalidas.
Sir, actually, I have one doubt. Sir, you talked related to the concentrated solar photovoltaics.
Yes, yes, yeah.
Sir, in that, usually what kind of material they'll use, sir? Usually, normally, there will be some silicon-based material will be there, or thin film technology-based material. But it is concentrated means the temperature will be higher. One side, you are giving the heat sink for cooling purpose.
Yes, yes,
So,
right.
my doubt is, uh, what kind of material instead of that thin film, what they will use, sir?
What type of material for what? As a, uh, I mean, as a
Usually,
concentrator or as a
yeah,
solar
yeah,
cell?
usually, yes, sir. Usually, in that solar panel, there will be a glass and encapsulant and a cell will be there. Again, encapsulant, then some material called PFE will be there. Usually, in normal
Good.
solar panel.
Mm,
So, in
okay.
case of concentrated solar, for the temperature will be very higher.
Yeah, yeah, sure.
Uh,
Yeah,
uh,
exactly, exactly. The temperature will
uh,
be very high. And
yes,
what
sir.
we have observed, we got 500 degrees Celsius see the temperature. So I'm working at 25 degree, and in my hand is 500-degree temperature. Can you see the temperature gradient difference? It's a huge. Now what we have done, we used the graphene as a, I mean, some modified graphene as a coating, or as a another layer in the top and the bottom of the cell. So
Okay.
whatever the heat is extracted or generated, they can be absorbed by the graphene. Okay,
Okay. Mhm.
this is the innovative solution. What is the traditional solution? They used some water, simply a water. Okay,
Okay. Yes.
they
Yes.
use simply some water. You can just put some water channels under your cell. So water is easily heat dissipate. But the problem of water is it's too slow, and you need a continuous running of the water. Now, to a modern technology, or in a modern way, you can do some graph, because there is now graphene available, right?
Okay.
Or very okay, or so you can use some graphene based coating or graphene related coating. Now you can ask me, sir, graphene is very expensive. How can I get it? Now you think that is your duty to think that how you can make a sustainable graphene. Maybe you
Okay.
can use some natural resources where you can get a easily sustainable graphene, right?
Okay.
Like we use some cotton shoot. When you burn a candle,
Yes, sir.
when the
Yes, sir.
candle is burning, you can get the carbon. It can be form of a graphene. I mean,
Yeah.
it's
Yeah.
just a thinking level. So you can use. So your answer is you can use some graphene material or any high thermal conductive
Yeah. Yeah.
material that can absorb the heat quickly. Yes,
Actually, I
yes,
have
you are
used
right.
graph.
There is a huge
Yes, sir.
temperature enhance.
You are right, sir. But actually, I am also working on nano fluids, which has higher
Yes,
conductivity.
yeah, that
So
is my second.
yes, sir. Yes,
Yes,
sir.
you.
I have
Yeah.
awareness on that, sir. But what I am asking is whether that cell I am asking whether that cell is a silicon based cell or normal PV cell only we are using.
Doesn't matter. Your cell is
Oh,
just an example. It is
okay.
silicon, it is perovskite, it is any cell, doesn't matter.
Okay. Okay. Okay.
Cell is a reference. Your cell is your reference.
Okay.
Is most importantly whatever cell you can use easily. But the thing is how you can extracting the heat. That is
Okay. Back to
important.
that.
You can start with silicon because silicon is easily available. But
Yes, sir. Yes.
we choose you why we choose perovskite, because perovskite's efficiency is quite higher compared to silicon. So
Okay.
initially the efficiency itself high. So when you integrate with a concentrated system, it will be automatically high, right? So
Mm.
high and high, rather than low and high. You understand?
Okay.
So in
Yes,
this
sir.
way it works. But you can start with silicon. There is no problem.
Okay, sir. And one more doubt, sir. Actually, whether we have to use Fresnel lens or point focus, which concentrator you are using, sir, in the top side for
Oh,
focus?
it depends. It's the sorry, I forget your name. Kalidas, right? Yeah.
Yes, sir. Yes, sir.
Yeah. It's a very interesting questions, but technically it depends. You can use Fresnel lens. You can use high concentrator, low concentrated, CCPV. I'm using those terms because I think you're familiar with that. CPC. Different types of lens are available, but you have to think what you want to achieve. You just want to achieve high current, or you want to achieve high current, but long-term exposure, something like that. So it's just not
Okay.
straight away. Yeah, it's up to you. So
Okay.
Fresnel lens is the common one, but
Okay.
there are other types of. But the problem of Fresnel lens is, I'm telling you now, it's a material side. Fresnel lens is a glass based, so definitely if anything based on glass is fragile, at the same time it's heavyweight. The
Yes.
size and the weight is high. So for example, if you want to make say this type of cell and this type of lens, it becomes very high. Now if you use the lower concentrator, CCPC, HPCV, this kind of, they are mostly PMMA based, which is a polymer. This is a
Yes.
transparent polymer. So when you transfer glass to polymer, automatically the weight, everything is getting reduced,
Yes,
right?
sir.
And it's cheaper also. So that is why it's up to you. If you're happy with heavy, then go for heavy. If want
What you are
light, then
saying
light.
is, sir, 1 minute. So what you are saying, already I use the same material, sir. That PMMA material, that is in some 5 thickness glass. Not it's like a sheet
Okay.
only, double sheet.
Okay.
I have
Then
used
then
that for the solar thermal conversion. I used for the evacuated tube collectors.
Yeah. Very good, really good. But the thing is, think something out of the box. Think something novel. Otherwise, it's difficult to publish a good paper. Because everybody knows. See, this is very common. If you put a lens under a solar cell, it will increase the temperature and it will increase the efficiency. Fine. There is no new science. But what is the new science? That as a researcher we need to find out.
Yes, sir. Okay, sir.
Yeah, think like this way. Yeah,
Okay, sir.
it is already established thing. Repeating is not a science. Established thing, that is this. I'm making enhancement, something, add something, that we try something. If we can replace, for example, we are now thinking how butterfly. I give you an example, I guess, during the biomimicry stuff. Butterfly wings. If you look at the physics of light physics of butterfly wings, how butterfly concentrate the light and gives different types of color out of
Yes.
it.
Yes.
Use that technique and make some optics regarding that.
Okay.
Yeah. Now here is not the importance of butterfly, which butterfly I should use. No, the importance is how a butterfly is actually transferred the light in such a way it can generate a beautifully colored their wings.
Okay.
You use this technology into solar cells also, that how different light can be entrapped, and end of the day you get more power, because sometimes we lose the NIR light, sometimes we absorb the UV light, different categories of wavelength we are playing with. So a solar cell, that is what not 100% efficient, right? So try to adopt that idea.
Okay, sir. It's a very
Just a
insightful,
just a
very
suggestion.
interesting
Yeah.
population, sir. Actually, I am working on solar thermal conversion. So you are
That
given
I
some
understand. Yeah.
in future. I will work in that solar PV conversion.
Mm-hmm. All the best,
Okay,
Kalidas.
sir.
Yeah.
Thank you. Thank you. Thank
Thank
you.
you.
Thank you.
Thank you
Thank
for
you.
asking question.
Thank you. Thank you. Thank you. Sir.
Yes, any more, or I think someone called Durga Prasad. I'm not sure. Yeah. Okay, if there is no more question, can I leave?
Okay, sir. Thank you very much, sir,
Okay.
for
Thank you.
spending
Thank
your
you for
time and
inviting me.
effort with us. Thank you. Thank you, sir.
Yeah. Thank you. Nice to meet you
Thank you,
all.
sir.
Have a good day. Good night.
Good night, sir. Thank you, sir.